Welcome to the lesson on electric fields and voltage. In an earlier lesson we discussed the electric field around a point charge, E is equal to kq over r squared. Another type of field is the field created between two parallel charged plates, as shown below. In the very early 1800s, after Alessandro Volta developed the battery, scientists discovered that a stable and uniform electric field could be created by attaching two metal parallel plates to each of the terminals of a battery. Here we have the top plate, bottom plate. Bottom plate is attached to the positive terminal. The top plate is attached to the negative terminal. The blue lines represent the uniform and parallel electric field. In physics, we define voltage as a potential difference between two charge points or between two positions in a circuit. In the diagram below, if electrons could move from the negative plate to the positive, each electron would lose potential energy as it gained kinetic energy, accelerating across the electric field. The change in energy per unit of charge is called the potential difference. So an electron would start at the top and would accelerate towards the bottom. As it accelerates, it loses potential but gains kinetic energy. This change in kinetic energy per unit of charge is called potential difference. The battery supplies a uniform voltage between the lower and upper plates. Any test charge placed between these two plates would experience an electric field strength, E, in newtons per coulomb, that can be calculated by dividing the potential difference from the battery by the distance between the two plates, giving us volts per meter. Note that the units newtons per coulomb are equivalent to the units volts per meter. Between the two plates, the electric field is uniform, and any charge placed anywhere between those two plates will experience a field strength calculated using E is equal to V over D. Only at the edges of the two plates does the electric field curve and give a non-uniform value. Note that the units of the electric field are newtons per coulomb, or volts per meter. These units are equivalent. The units of potential difference, of course, are the change in energy per unit of charge, and these are in joules per coulomb, or volts. If we take the top equation, E is equal to voltage divided by distance, and solve for voltage, we of course get electric field strength in newtons per coulomb times meters. A newton times a meter is a joule. And of course then we have coulombs on the bottom. And a joule per coulomb is equal to a volt. At this point, you should review a number of problems and applications requiring these equations to find solutions.